Welcome back, everybody. This is our second video in this series, and we're going to talk about partial derivatives. It's our second video in the lab series, and we need to deal with the situation that we might have a function of more than one variable. So last time we talked about the derivative and how we take the derivative when it is a function of one variable, but now we might have a function of multiple variables. So what would that look like? Let's say we've got f, which is our function, and it could be a function of, we'll go three variables for this one. X is one, y is another, and z could be our third. So this is, f is a function of multiple variables. And now I need to know how f is changing. And specifically, I want to know how it changes with respect to just x. So I want to find, I'm not trying to find how f is changing with all of them, but to find how f changes with respect to x. And I do that with a partial derivative because I'm only looking at how this function of multiple derivatives changes with only one of the derivatives. So it's just a partial derivative of that function. And the way we denote that, our notation for the partial derivative, we do this with a partial derivative. And you'll notice that it looks very similar to our full derivative, but instead of having the straight line on our d, we now have curly lines on our d. So it's this curly d like that. And the way this reads is this is the partial derivative of f with respect to x. That's how we would say this. This is the partial derivative of f with respect to x, where it's understood that f is a function of more than just x. It's a function of multiple variables, and x is one of those variables. All right, so how do we actually do this? All right, this may sound intimidating. This is a topic that you'll cover in your Calculus 2 class, but it's not that bad. And we're actually just going to do an example. We're not going to derive anything. We're just going to jump into a couple examples and let you see how we do this in action. And from there, hopefully it's not too bad for you. So let's say that we've got f is a function of x and y and z, and we'll pick an example here where this could be, I don't know, we'll go x squared multiplied by y, and maybe we'll divide that all by z cubed. All right, so we've got a function where we've got x and y and z, and it's all in there. And we need to take the partial derivative. All right, we want to find the partial of f with respect to x. All right, now when we do that, we've got these other variables, y and z cubed. Well, if we're looking at how this function changes with respect to x, we're going to leave these other variables constant. We're not going to change them. So we're going to treat them like constants, which means they just come along for the ride. We simply pull them down. We don't change them. That was z cubed, not z squared, so z cubed. We don't change them. We don't do anything to them. We're not plugging them into anything. We simply pull them down. We're treating them like they were constants being multiplied by our function. And now we have to take the derivative of this x squared, and we're going to do that the same way we did before. And if we remember from our previous video that the full derivative of y with respect to x is equal to n times x to the n minus 1 when y was equal to x raised to the n. Well, now n is 2 again, which was the example we used in our last video. And so when n is 2, this is going to give us 2 times x to the 1, which is 2x. And if you remember in that example, the derivative of x squared is just that. It's simply 2x. So we're going to multiply it by the derivative, essentially, of just the x part. All right, we've got this, and we can simplify that out just a little bit if we would like. The partial derivative of f with respect to x is equal to 2 times x times y divided by z cubed. That's how we do that derivative, and that's the answer for that partial derivative. It's that simple. All right, let's keep with the same example, and let's find the partial now with respect to another variable. Let's find the partial of f with respect to y, which is another function of that variable. Well, just like before, we're going to look at y, and we're going to take all the other variables and treat them like constants. So this x squared divided by the z cubed, that part just comes along. All right, that is treated like a constant. So we don't change that, we don't manipulate it, we don't do anything to it, we just simply bring it along. So there's the x squared times the z cubed. And now we're going to multiply that by the derivative of y. Well, the derivative of y with respect to y is 1. Right? The derivative, how does y change with y? Well, that's a 1-to-1 value. It just, and you can think of it even here with our term, because y raised to the 1, well, if n is 1, I pull the 1 down and I multiply that by y times 1 minus 1. Well, 1 minus 1 is 0. Anything raised to the 0 is just 1. So I'm left with simply 1. So again, we can simplify this down, and the partial of f with respect to y is going to be equal to simply x squared divided by z cubed. That is our answer for that partial derivative. And we'll do one more in this video. We'll take the partial of, we'll find the partial of f with respect to z. All right, we'll find the partial of f with respect to z. Well, in order to do that, we're going to rewrite our expression for f just a little bit. We're going to rewrite our expression for f just a little bit, and we're going to rewrite it this way. We're going to remember that this is also equal to x squared times y times z raised to the negative 3. So something in the denominator being raised to a positive value is the same as that thing in the numerator being raised to a negative exponent of the same magnitude. So this is the same thing. This is just f, and we've rewritten it. And we've done so we could take advantage of this same rule, where we now are going to have n for this, for z, n is going to be equal to negative 3. So we can take and use the same rule. And we'll pull the negative 3 down in front, and we'll raise it to the z times negative 3 minus 1, which will give us a negative 4. And we're going to do just like before, and we're going to treat the x squared times y as a constant. So this is going to be x squared times y, and we're going to multiply that by the derivative of z to the negative 3, and the derivative of z to the negative 3 will be negative 3 times z to the negative 4, right? We just simply take the negative 3 down, take the negative 3 down, and then subtract 1 from that negative 3, and it becomes negative 4. And we can rewrite this in the following manner. This can simplify a little bit. This is negative 3 times x squared over y, and we can put that z back in the denominator and rewrite it as z to the 4. And that is, in fact, the correct answer. And that's how you do a partial derivative. This is going to be super important to us as we continue in our lab program and we get into something called propagating uncertainty, which you will do in nearly every single lab class. You'll have to propagate the uncertainty, and we have a tool for that in our Appendix D that you'll become very familiar with in our lab program, but you'll need to be able to do these partial derivatives. And so this video hopefully will now serve as a resource as you prepare to be able to do that. All right, and we'll talk to you later.